Hi, I am Souraja Kundu. Today I am going to present my DA63 course project on climate modeling using multimodality satellite images. The motivation of this project was that because of the training of huge deep learning models, there has been lots of carbon emission and consequently global warming. So I want to use AI for modeling that how climate is changing over the years. From the broad term climate, I have chosen the term cryosphere, which means the world's frozen area, specifically the India Himalayan region, the high altitude regions where the snow cover is gradually melting over the years because of increased temperature and humidity. I want to model that how the snow parameters are changing with growing carbon emissions and the with years. So firstly, this project is multimodality because on one hand I'm using multimodal satellite images. I'm collecting optical images, the green, red, blue bands, and also shortwave infrared ray and near infrared ray bands. And I'm also using synthetic aperture radar or SAR images. These are very useful to capture images even during night or in cloudy conditions. And these actually can give very high resolution images. These are images, RGB images, and also I will derive some snow cover masks using two different indices. One is normalized difference snow index or NDSI, and another is normalized difference fractional snow index or NDFSI. So using these three images, I will create my image dataset, which are multimodality images or of different frequency bands. So that's why multimodality. And also, this project is multimodality in the sense that I am using the climate parameters, which are some numerical time series data. And I will correlate a time series data with some images. So that's why this project can be classified as a multimodality one. And another thing where the multimodality comes is that when I try to visualize different feature maps of the images, I use the vision part of different vision language models or large multimodal models, LMMs. For using that, I had to read different state of the art vision language model papers, and also different multimodal learning papers, and I really enjoyed learning those. So back to my project. I collected the data. The SAR images were collected from Sentinel-1 C-band images. Um and the optical images were collected from Landsat 8. I used Google Earth Engine for collecting those, and mainly of two regions. One is the Arunachal Pradesh region, and another is the west of Karakoram mountain region. And I gave different latitudes and longitudes over the years from 2014 to 2024, and throughout the year for different months I collected the data, and there were 4000 plus images, but many of those images were not of size 512 cross 512, and there were many other issues for which I had to delete those data. And this is the curation process. After the dataset curation, the dataset size reduced to one third, only 1048 images. And now I have the triplet images, and I also use the Open Meteor Archive API to collect climate parameters. Climate parameters like the temperature, humidity, precipitation, snowfall, etc. And after that, I have paired the whole dataset, and I plan to open source it. And there is one example of the SAR image. I initially explored different ways to collect the images of SAR, but finally I stuck to Google Earth Engine. And SAR images have also inherent spectral noise due to the acquisition process, which is a multiplicative gamma distributed noise. And for removing that multiplicative noise, I initially in this semester trained that this despeckling model, and got better accuracy using the linear angular attention transformer in linear time than most of the deep learning models. I submitted that work. And next I show this RGB image, and this is green NIR and SWIR. Three bands are there in this image, and from this right side image, I could derive this NDSI and NDFSI masks using the green NIR and SWIR bands using the some formula of fractional difference. Uh, but my proposition is to use NDFSI mask because it's more continuous, more smoother than the NDSI mask, which is a bit noisy. Um So after the collection of the dataset, I proceeded to segment the images, and for segmentation I used unit and also segment anything model. For I trained the unit from scratch, but the accuracy was not very good, because over the epochs the training loss was gradually decreasing, but the validation loss was slightly decreasing. Therefore I can conclude that the model is, there is actually overfitting. But although the validation accuracy was increasing, I predict that since the RGB images, because snow cover masks are extracted from RGB images, and the SAR images are of very two different domains, of two different frequency bands. That's why the internal representation and hidden representation of these two images are very different. To learn that, I need more number of trainable parameters, and since this unit is very small, a few million parameters, so I went to the segment anything model, which had multiple billion parameters. With unit, the dice coefficient accuracy on the test dataset was 0.48, but after inferring on my test dataset using the pre-trained vision transformer encoder based segment anything model, I got the test accuracy of only 0.49, which is not much improvement. So I went on to analyze what are the different features of the SAR and RGB images that are distinguishable. So for that I went to some image encoders and also the vision part of some visual language model like clip and the contrastive language image pre-training and dynavi to deep lab v3. These are the image encoders. So first I plotted the clip embeddings. I reduced the dimensionality to 2 for visualization and took 4 SAR images, 4 RGB images paired, plotted them, and I can see that the embeddings are translated or shifted. So from this I get a future research direction in which for using this paired RCR RGB images I need to use some kind of contrastive learning for aligning the embeddings. So this can be one future research direction. Um, and I also tried to plot the feature maps after each of the main blocks of clip, and I saw that over the time it is focusing on particular regions based on depth. And also we know that with depth the snow cover also changes, higher depth has more snow. So using this kind of feature extraction technique of clip, one can also use it for the encoder part of the unit or some kind of segmentation model. So next, I wanted to compare one SAR image and RGB image and see that how those features are different. So I plotted Fourier spectrum using FFT and saw that the SAR image has higher frequency content than the RGB image. And another thing I noticed that for the SAR image and RGB image, after each block of clip, the feature maps are very different. Even though I collected the images at the same location at the same time, the feature maps are different, and that was the reason why the segmentation models were not performing well. And of course over the time the activation map is changing for clip. And next I use the deep lab v3, which uses the resnet 50 as its backbone. And DeepLab V3 also uses some dilated convolution layer and multi-resolution pyramidal pooling layers for higher, better quality feature extraction. And for the DeepLab V3, I also plotted the feature maps after each layer of this RGB and SAR images, and I can see that the feature maps are very different. And of course, over time, the focus is going mainly for different important regions. Like I can see in the RGB image, the orange color is mainly the snow. Next, I went for Dino V2, which is another image encoder. And here also, I can see that the feature maps are very different and they are also changing over time. Next, I went for a climate modeling task. That is, for this many coordinates, I collected this temperature, precipitation, snowfall, relative humidity, snow pixel count. Snow pixel count is from the snow mask. I calculated how many pixels are black, dark, zero. So that snow pixel count will be proportional to the snow covered area. So I plotted the snow pixel count versus all these climate parameters and observed a very strong linear correlation between these parameters. So I ran a linear regression model as was taught in the class. And after that, I see some very intuitive results that with temperature increment, the snow pixel count decreases. As precipitation or snowfall increases, the snow pixel count increases. As humidity increases, snow pixel count decreases. So these are very intuitive results which I can see also or visualize from the data. which is very convincing. Another convincing thing is that I plotted the snow cover mask over the year, so I can see periodical variation over the seasons like summer, fall, winter, spring. The snow cover amount also periodically changes. Another thing I plotted is the temperature variation over the years. It is periodic, but it is actually increasing. So I tried to fit one linear regression model, and as I can see that the linear regression, the line has a positive slope. That means the temperature increases over the years. And I also initially saw that the snow cover mask decreases as the temperature increases. So with this, I can finally convince myself that over the years the snow cover mask has reduced. So that's how my climate modeling aim is satisfied. And I also enjoyed doing this project because all the waking hours of the past 4 days were spent in reading different articles. I read about multimodality neurons and different multimodality learning papers. I also did this project coding, etc., and I am satisfied with this project. Thank you.